So this afternoon, we're very honored to have Professor Jason Ren to give us a talk. This is also a part of our center's webinar series. Professor Jason Ren, he is currently a professor in the Department of Civil and Environmental Engineering, and he's the Associate Director for the Andlinger Center for Energy and the Environment at Princeton University. So he leads the Princeton WET Lab, which is water and energy technologies, with the research focus on water and wastewater sector decarbonisation and digitalisation. So his group uses electrochemistry, microbiology, and the data science tools to understand the fundamental determining factors and develops new technologies for resource recovery during environmental process. So Professor Ren has received quite several big awards, including the 2020 Walter Huber Civil Engineering Research Prize from the American Society of Civil Engineering, and also 2021 Paul Bush Awards for Water Research Foundation. So, of course, he has published quite lots of high-impact papers. He also co-founded 2 companies with students to translate research fundings into real-world applications. So thank you very much, Jason. So shall I just hand over to you? So his title for the talk is the decarbonisation and digitalisation of water and the associated industry.
Thank you so much, Eileen. First of all, it is my honor to come here to Loughborough and the UK to really meet all you distinguished researchers in person, and it's been a lovely visit so far. Also I'll be very glad to share some of the research we've been doing in the past few years, especially on the decarbonization and circular economy side of water and chemical sector. Recently we started really to think about how do we also, along the sort of circularity of the water sector, how do we digitalize and modernize it? Again, thanks for coming, and thanks so much, Eileen and Jean, for the invitation. It's been a very pleasant visit so far. So let me just use probably 2 minutes to talk about our center. So the Andlinger Center for Energy Environment actually was the reason I went to Princeton. They recruited me to really to look into the between water and energy interface. And our director is Lin Lu, who has been on sabbatical, extended sabbatical in Singapore, founding a new maritime center for decarbonized shipping. It's a big initiative. So I took over as acting director for more than years. I recently stepped down, go back to my research director role, but I do want to introduce to you that this is really the premier place for Princeton to really getting into energy environmental research, and we basically embrace all sort of topics. As Princeton is a very small university, I have to say. It's about 800 full-time faculty members. And in terms of energy environment, we cover the built environment, transportation, electricity-related, fuels and chemicals, environmental, which is mine, certainly public policy, which is a big deal at Princeton, and then the natural science side of it. You probably know we had 3 Nobel laureates actually were inducted last year. One from Scotland, actually. David Macmillan was really chemistry faculty, and Professor Manabi was a professor in physics, so they both actually doing actually climate-related, energy, environment-related research. David was really on the organic molecule side of things. There's 14 core faculty, so we're half pointed. These are hard-aware actually FTEs. A quarter of the faculty actually of Princeton actually associated with the center. We have visiting fellows. These are visiting professorships. They are paid. It's competitive based, but for your sabbatical, if you want to visit Princeton or US. And we also have distinguished postdoc fellows, also paid, if you want to spend 2-3 years at Princeton doing certain research, and certainly graduate fellowship and things like that. We are sort of expanding greatly in the past 2-3 years on industry partnerships. So these are our industry partners. You can see they really span from many different industries. We have big energy industry, we have consulting industry, we have tech, we have utilities, and sort of many sort of different, I guess, areas really to get into sort of collaboration between academia and industry. All right, with that said, I just actually copied this news image from BBC today. It's basically asking a question. Many of you probably can answer better than me on where we go in terms of climate change, but more specifically in terms of water. And I know you guys just had the record. I don't know if this record number, but it's a credited source, right? Last month, that the hottest day ever, right? And then when you think about U.S., it's really on the same line. So on the right side, on my right side, is the East Coast, where I am from. Generally, as you see, just last month, we had a big flood in Kentucky. More than a dozen people lost their lives. And New Jersey, New York, and most of the East Coast had many hurricanes and floods, flash flood especially. So you get wetter in general, the trend. On the West Coast, as you see, Nevada, Arizona, California has been extended drought. And then the fire, a lot of people had to flee from California to somewhere that they don't have fire. In fact, sadly, my old house, when I stayed 10 years in Colorado, was burned down like last year because of wildfire. I sold it, but unfortunately. Anyway, so just give you the sense, when you think about all these climate-related events, right? We used to call really extreme events. They are all associated with one thing, which is water, right? Either we have really very short period of time, we have too much water, we have extended time, we don't have enough water, we're just in the wrong place and wrong time. So with that, let me say water is something we have to manage on the water resource side of it, and also on the quality and quantity of utilization side. So then how does that, from engineering perspective, related to energy? This is the report recently by IEA, saying among all the different water-related activities, whether it's treatment, transfer, distribution, supply, desal, about 4% of energy, global energy, electricity is used in water-related activities. And on the other side, you see this is a 500-page report by U.S. Department of Energy, really to looking in the interface between water and energy. They are very interdependent, as many of you know, and certainly tightly related with climate change, land use, and many other things, right? So I won't really give too much of a big picture on water energy interaction. Are you all expert on that? But then what I want to pivot is that I am a environmental engineer, right? But nowadays I do a lot of chemical engineering work. Way I have to say, because chemical engineers just say, hey, environmental engineer, you just deal with the mass we discharge, right? Or human beings, or whatever waste that we generate. So that's actually a mentality I was trained for when I was a student too. But in many cases, when you think about who can manage carbon better, go back to Dr. Xuan's opening remarks. When you think about circularity of carbon, if you want to really keep the fossils underground, you have to circulate the carbon. So where does the carbon come from? How do we circulate it? CO2 is one thing, methane is another, right? That's a gaseous phase. There's a tons of actually liquid carbon in wastewater. We all contributed to it, right? And then there's solid carbon, right? Whether it's municipal, agricultural, or industrial. And certainly there's the biomass, right? The trees, the grass, and the marine biomass, right? So those are the carbon we have to recirculate back in order to make it actually balanced, right? Many of you are microbial electrochemistry experts, so I really won't get into too much into it. But really the thing is the benefit of biology and electrochemistry is that you can really take advantage of the renewable energy right now and also use what nature does, that's what biology is, to really circulate how this carbon being utilized and consumed back, right? So I'll start with organic carbon, waste carbon, and then we'll talk a little bit of CO2. There's another report I was involved in by US DOE, basically looking into the potential of the organic carbon embedded in the waste materials, where for the primary waste material that had a high carbon content, whether it's a wastewater sludge, food waste, animal waste, or fat oil and grease. And when you think about that, there's about 11 billion gallon gasoline equivalent of carbon in there. If you convert them into electricity or actually fuels, that's about 8 to 10% of gasoline use in the US. The good and bad news is since this year, this area has got a lot of attention and interest because the gasoline price has risen so much, right? So it's become so competitive. So for many of you doing techno-economic analysis, it's become more competitive or viable in that case. So in the water industry, there's really a paradigm shift where when you think about waste, it's no longer waste, it's energy-embedded chemical that if you can really recover a fraction of the energy, you can make this industry carbon positive. In fact, why US DOE or Department of Energy really look into this wastewater industry or waste industry first because it holds the most potential, low-hanging fruit to make this whole industry energy positive. And then when you think about, there's also possibility of making carbon negative because we discharge trillions of gallons of wastewater each day. We can capture CO2, and then we can make a profit of it. Talk about the economy side of it after all, right? So there's really a lot of things we can do. Just to give you a quick example where what can make a difference. Think about New York City as an example. The city has 14 treatment utilities, and it's consumed 480 million kilowatt hour every year, emits hundreds of thousands of tons of CO2 due to burning of fossil fuels, and drain more than $500 million for treating the water, and certainly in such a premier actually land, nobody wants to live nearby. But if you would develop different technology, which I'll talk about fuel, that to generate energy, capture CO2 and methane, and then generate revenue by selling the product of the resource, that you may be able to achieve all three goals. It's a long shot, but we have to think about it, right? So, all right, so go back to electrochemistry, my favorite subject, right? When you think about, again, from the environmental and chemical perspective, when you talk about electrochemistry, it's basically electron donor, electron acceptor, and that same thing actually also true in biology, right? So whatever we do, like we just had a wonderful lunch, right? Whatever you eat, it became sugar in your blood, right? And that's our electron donor, and then we have to breathe, that's our electron acceptor, it's oxygen, right? What do? We have to actually, if there's one chemical I have to deal with, for example, organic matter, they have to provide electron acceptor to couple it, right? So, and then on the other side, if you have electron acceptor contaminants, then you have to provide a donor. The unique feature of the electrochemistry or electrode is you actually can play with it to use it as either a donor or acceptor. So in that context, when you think about the greenhouse gases we have to deal with right now, CO2 and methane, they are on the two extreme end of redox tower, right? So one is the most oxidized one, very inert. The other is the most reduced one, also inert. What we are trying to do, everything, this whole center, right, in UK, and many other people are trying to do, is basically either reducing, oxidizing, using electrochemistry from cheap renewable electricity to produce anything in the middle, right? So that's really, whatever catalyst you do, that's really something we think about on the sort of feasibility side, play with electrochemistry, right? Again, you can, on the anode side, this is a very complex stuff, but basically you can oxidize things. On the anode, in my case, it's a wastewater, or anything that we don't want, to get electrons out. Then on the cathode, then you can use electrons to reduce CO2 and other things. So there was a review basically telling us, okay, there's so many different chemicals we can produce through such different process, whether it's genetic modification or whether it's natural microbiome, this is biology side of it, to convert organic carbon into a variety of chemicals that maybe right now we use a petrochemical to do it. Then on the CO2 side, you see all these reduction equations, again with different potential, different amount of electrons, you would be able to produce a different level chemicals, right? So my view as a process engineer is that you cannot, for many of the chemists, I have to say, or material scientists, they focus on one thing. They focus on either the catalyst side or material side. This side won't work. This side works. Anyway. They would focus on the cathode, say whether it's a hydrogen evolution or CO2 reduction. But I would argue you cannot only assume that you always have clean, fresh water to support the water electrolysis all the time, right, on the anode. So can we also co-valorize the anode by basically oxidizing the organic matter, whether it's wastewater or other things as an industry byproduct, to provide the electrons, reduce the junction gap, and then achieve both anode oxidation and cathode reduction. All right, so let me give you a few examples. One is hydrogen. U.S. just launched a $8 billion hydrogen hub call. Everybody got energized, honestly, hydrogenized, to be honestly. Okay, that's a big deal, right? Because we realize that electricity or battery cannot solve everything we use for fossils, right? That's why hydrogen came to play. Not only can sort of complement some of transportation sort of deficiency battery cannot do. For example, some of the long haul trucks or shipping and other things, but also most importantly, I think is really on the chemical industry, energy storage side, and also chemical industry, because a quarter of the petrochemicals we use come from current basically chemicals from petrochemicals, right? So that's sort of one thing. And then when you think about CO2 reduction, to get to hydrocarbons, you got to have hydrogen, right? So that's sort of one thing. We did also a review or calculation to basically say, okay, if you have all this assuming renewable, cheap energy globally from weather, solar, wind, biomass stuff, how much hydrogen we can produce, and then how much CO2 we can remove. So it turned out to be a lot. So that does sort of prove that hydrogen can be a very interesting product we can have. All right. So that's one sort of I guess idea. What we did was, when you recognize again the co-valorization idea, is if you do hydrogen evolution on the cathode, you need a 1.23 volts. Theoretically, in general, you need a 1.6 above. But if you would replace your anode reaction from oxygen evolution, water oxidation, to organic waste, you would really shrink the band gap by about 90% to about 0.12 volts, right? And then if you add a little bit light in there, oops, you would be able to produce pure hydrogen pretty nicely. So it's visible light with a photocathode and then a bioanode. So in that case, you got pretty good current density. Light on, you have current. Light off, you don't. Then you have a stable potential. And then you have a pretty good current density, about 20 milliamp per centimeter square. We were the first one used it in real wastewater, brewery wastewater. Not whiskey yet, but because again, it's very sugary, it's easy to operate. To basically really argue, you cannot really always use pure water on the anode and cathode to deal with all this electrolysis, right? And certainly one trick was on this photocathode is used to black silicon. It's quite stable with the Swiss cheese structure and without much degradation. I have to admit that we didn't do this. This is a collaboration with the chemical engineer. One other thing you may say, well, we generate wastewater 24/7, and you cannot just treat it during daylight time, right? So that's why we coupled it with a little power management system, PMS, where basically we decoupled the anode and cathode reactions. We were able to boost the little voltage from the anode from 0.35 to 2.2. So in that case, you have enough voltage to, to get the hydrogen out, right? So that's where you see a 24/7 non-stop hydrogen production out of wastewater without even light, without any external voltage, right? They're basically self-sustaining. When you put in wastewater, you got hydrogen out. We do have some loss in that case, because when you have high voltage, you sacrifice current, right? So hydrogen evolution was pretty efficient in terms of cathode efficiency, 90%. Then we did have some loss on the converter side that we're working on to optimize it. Then when you think about, okay, similar idea, can be used in CO2 reduction. So in this case, your CO2 voltage is 1.34 theoretically. It's not too bad compared to hydrogen, but the overpotential is very high, right? So we cannot do either, meaning only light or only circuit. So we had to have both to basically make up the junction of 0.24. So in that case, we produced twinnable syngas, CO and hydrogen mix. Why we had a mix in this case is because, again, that's what I felt electrochemistry has a limitation, because we can, right now at least, we can only produce one carbon or two carbon sort of products more efficiently. For Chi elongation, like a carbon 3 and above, it's very difficult. That's why credit to actually Shell's support and also the Department of Energy, we are trying to say, can we actually have a hybrid process where we can produce twinnable syngas, because the bacteria we chose, Clostridium gondalia, when you have a higher hydrogen, they need both. When you have a higher hydrogen, they tend to produce more acetate. When you have higher CO, then tend to produce 2,3-butadiol, which is a much higher value product. So if you would be able to twin it very, easily, just with the potential switch, you would be able to produce a twinnable products out of the biological reactor following the electrochemical one, right? So that's why at the moment we sort of delivered this twinnable gas out of CO2. We have a gas diffusion electrode of that. And so basically to get to biocompatible electrolytes for growth, then you see we were able to get to different voltage. You do see actually twinnability between the ratio. So that's a sort of still going on the biology side of things. Then we realize, okay, look, electrochemically, biologically, we can produce all these different organic materials, right? Most of them, like say volatile fatty acid, for example. Then we have a mix. How do we separate it, right? So how do we separate? I mean, the interesting part of the separation is you have to deal with a lot of sort of volatility, like whether it's a gas, ammonia, or volatile fatty acids, or methane, CO2, any things, so you can extract them out, or you can have a higher delivery of CO2, for example, or hydrogen for your organic acid extraction, right? So in that case, we sort of, during COVID, again, we were locked in out of the lab. So we're basically doing, okay, is there a way we can understand what kind of different acids we can produce out of CO2 or out of organic matters? How do we actually design membranes to have a better separation to get these volatile fatty acids out more effectively, right? So we talk about different membranes, whether they use pressure-based, volatility-based, again, ROFO and nanofiltration, evaporation, membrane distillation, all sort of different things. How can they develop better membrane to get things out more effectively? Because right now, most of research has been primarily focused on the producing side of it rather than the separation side of it. So that's links to some machine learning work we've done. So this is sort of a very, I see, random graph. Basically what we did was we extracted literature about nearly 1,000 articles that talk about membrane design, mostly manually, for acetic acid extraction per evaporation. And then we use a bunch of machine learning methods to say, okay, can we find any trends? Because if you eyeball it, you cannot really do anything. So we basically say, okay, can we use machine learning methods? We turned out a random forest was a better one to identify the most critical parameters that can design better membranes for us, right? So we end up finding the mass ratio, atomization energy and feeder concentration really on the top three side of things that would affect the membrane design and the separation much more than others, right? So they sort of basically use all these tools to help us understand what's going on in there. All right, one other thing we have to think, okay, we got CO2, for example, right? Well, previously we got oil, right? What kind of things we can produce makes the most sense in terms of economics, right? If you produce, honestly, ethanol, acetic acid, or formate, or even syngas, that's okay because they have big market size, but the unit value is not that very high. So we think, well, can we actually increase the margin of the products? So that's why we work with another colleague in chemistry to look into, okay, we basically converted CO2 into ethanol first, and then we divide this enzyme cascade, basically cocktail of enzymes, and produced a pharmaceutical, green pharmaceutical called statin. So it's a precursor that has a market size of $14 billion, gonna increase to about 17 in a few years. So that sort of give you the sense, okay, this is certainly has a much higher margin in terms of the conversion, right? The trick of that is certainly the enzyme side of it, but also the advantage of using enzyme engineering in addition to whole cells that we've traditionally been using is that whole cells, they will produce this very mixed products, right? Like I mentioned, like acidic, butyrate, ethanol, everything together, right? Formate. When you have a designed enzyme cocktail, you have a much higher specificity in terms of the product you get. And then you can design this enzyme to produce, I guess, a lot of different things you want beyond what the natural electrode or catalyst or bacteria can do, right? So that's why I see that's a very interesting direction that we may look at. All right, so that's what basically say acetyl-CoA, Wood-Gondal pathway using the cells can produce a variety of organic chemicals. Another route we have not touched upon today so far is mineralization. We talk about the CCUS, right? Carbonization of CO2, where you basically convert CO2 into calcium carbonate. Then this is sort of basically electrolysis process. Then you can also produce pretty high efficiency cement precursor materials, right? So that sort of also gives the things like not only the organic chemistry matters, but inorganic chemistry also can be very interesting. So with that said, though, again, go back to my water route. The current wastewater treatment does not really recover much. It basically treats the carbon, nitrogen, phosphorus as a waste, right? So So we spend a lot of energy, a lot of chemical getting in there, and then we end up basically have a cleaner water, and then sometimes we recover some methane. And certainly use a lot of chemical energy. So as a result, on the left side, you see they do emit a significant amount of greenhouse gas. This is the USA and China's data. And then we do pay a large amount of sewer bill. I assume all of you would pay that to run the treatment plant. However, if you would imagine the blue sky scenario, that's Rochelle's terminology, that you would basically be able to still remove carbon, nitrogen, phosphorus, but you can use electrochemistry, but you also can capture CO2, produce hydrogen, produce minerals, then you have a microbiology to deal with nitrogen and phosphate, you can produce biofuels and biochar. So in that case, you can have a carbon negative scenario, and then you can sell the products for profit. So that's sort of there's a possibility to make it carbon negative and a dollar positive, or pound positive, whatever you call it. All right, last two examples on this electrochemistry side is more very applied. It's basically we work with a refinery to look at ethanol refinery. So they have this what they call black liquor. So this is really black. Basically, it's a fermentation byproduct with a lot of sort of acid lignin in there. So we played with this microbial electrochemistry where you have anode degrade the organics, cathode you have hydrogen production. So you play with the pH in between to basically precipitate lignin out at the lower pH on the cathode. Then on the anode, then on the cathode you have higher pH due to hydrogen evolution, right? And then you would be able to recover all the different ions, right? Cation ions and ion ions. So in that case, you basically valorize this waste from an energy perspective of hydrogen, material perspective lignin, then acid as well. So that's sort of one example. Another one is funner. This was done by my former students, now CEO of a startup company. So we sort of co-invented this process. Initially we treated this waste beer wastewater. Now you know my favorite wastewater. So brewery wastewater. So it has a lot of sugar, starch, and things like that, right? So the fungus would be able to grow on it, clean up the sugar, and grow this sort of biomass. And then initially we were thinking, we talk about energy, right? We put in some cobalt catalyst down there, so fungus would encapsulate this thing to become sort of this metal-embedded sort of a graphenic sort of structure for battery. So we call it a beer battery, something like that, right? Very catchy name. Then, credit to him, he pivoted. He got $2 million out of our technology, founded a startup, and then he talked to Tesla, fuel cell companies, say nobody wanted to buy this battery because it's first of all, it's too expensive. Second, it's too slow to grow, right? Compared to graphite, right? However, what he found was this fungus has a very good texture and doesn't have any color, right? So what they did is they actually pivoted to produce artificial food, like Beyond Meat and Impossible Burger type of thing. However, they targeted high-end industry. So what they did, they were very successful. So they raised so far $126 million to really basically scale up the production and fermentation. The company is called MIDI. So it's sort of actually, I got a few samples a few months ago to taste it. It's actually not bad. It tastes like meaty, right? So it's meaty here. Anyway, so just to give you an idea, really what I'm very impressed in here in UK is the close collaboration between industry and academia. I think US needs to do more on that, and also the entrepreneurship. Because when you get students are really excited, he spent 6 years with me, master and PhD. Now you can see, many of your professors, you see the most satisfying thing is you see your students being successful, right? Whether they become professor or CEO. Even though I haven't seen a penny yet, all right? So one last project, what I want to talk about is really my newest passion. This is really inspired during COVID from a report from UK, Water UK, all right? you guys have the most aggressive roadmap. By 2030, the water sector needs to be net zero. 2030. Think about how many years we have. So what Water UK did, so they basically look into the first, this is the first one in the world. They should have promoted it more, or they give me credit for doing this in UK. Basically they look at all the greenhouse gas emissions associated with the water sector from the point where they draw water from river, for example, to the point they discharge back to the river, utilization cycle. What drew my eye was this part. You see, most of the other parts are dark blue, meaning they are electricity based. You can easily identify how much emission you have, right? This process emission is very interesting because it's a largely unquantified, meaning that 40% of wastewater emission is not known, right? There's very limited study on it, largely by modeling, and yet there's a lot of technology actually would do more harm, I have to say, than good. Think about some technology can recover methane, but majority, 90% of methane is dissolved in the water. If they discharge that water, the methane going to emit out to the atmosphere. It's worse, okay? Then the little methane they recover. Just to give you one example, nitrous oxide is another big deal, right? So what I really tried to do was really kindly quantify this. There's a lot of different sources of basically greenhouse gases during the wastewater collection system. Sewer is another big deal. And during the treatment. So I work with some air quality folks. So they do all this sort of electric vehicle sensoring on top of their car. So they do this for oil and gas. Very good sensors. So we drive around and we see basically mapping out the emission. This is a scope 1 direct emission. You see this is a digester, see how much emission you have surrounding the thing. So what we found, there's a lot of data I won't repeat, but what we found, so the actual emission based on the literature directly monitored data and the data we got, we actually surprisingly got a similar result where about more than twice of the emission estimate by IPCC EPA. So in short, it's basically at least twice of the emission that were associated with wastewater were actually emitted than the estimate. So in many cases, when you think about carbon circularity, you have to know how much carbon you emit first, right? Then you can go back to say, okay, what's the market potential we can do, and the text and the things we can do. All right, I think that's it. Last, I want to, shamelessly promote one open access book. The good news is free. If you are interested in any of the things related to water sector decarbonization, capture utilization, feel free to download the book. That's my co-WET project, basically. And then I do want to appreciate my lab member and our sponsors. Happy to take any questions. Thank you.
Thank you very much, Jason, for a really inspiring talk. So I'm sure there are lots of questions there. Right, okay. Let's start with Richard. Yeah.
No, it was an excellent talk there, and I work in a very similar area, so I'm very pleased as well. We've got huge challenges, so hopefully that as many people as possible working on them can solve them. So we looked at membrane extraction from volatile fatty acids as well, and we got it to work pretty well. The problem we had is CO2. It used to come across with acetic acid as well. Did you have a similar problem, or?
That's a very good question. We have not tested that, I have to admit. So far, the membrane what we've been doing was mainly from organic substrate. But that's a good point. We certainly need to discuss more or learn more from you. Yeah.
Because the other big benefit was you retain the nutrients as well, NMP, because we're looking at gas phase fermentations as well as traditional organic fermentations.
Yeah. You can do the droop heating or swing, and to do the ammonia and other things. We have a project.
And we also have problems with lipids as well. So
that's cool.
Some wastes are very lipidy and oily as well, and greasy. But
super.
Yeah. you.
Thank you.
Okay, well, that's
It's very nice talk. So I'm asking about from a chemical engineering point of view. So you got nice science reaction there. How about the conductivity of this wastewater and even electrical and cathode assembly?
Yeah, right on point. I have to admit, many of you are MFC people. You probably agree. I've done MFC research for many years. Now you can see I sort of expanded more. The main issue of electrochemistry in municipal wastewater treatment is low conductivity, so the resistance is much higher. So you have to design this one very compact, and that's why industrial wastewater is much better in that case.
I think you're talking about the current density. It's also the geometry density.
Mm-hmm.
So probably you can do like use not mesh, use form, 3D electrical.
Yep, carbon foam, carbon brush, carbon felt, all those sort of things people used. Flow cell, a lot of people tried. One thing I have to say, there's always, when I talk about these things, even the Shell project, I was asked the question. I mean, your current density on the anode is so low, right? It's at least the order magnitude lower than our cathode, right? So how would you be able to match up? So I agree, it is low. It's been catching up by an order magnitude before. It was 2 orders low. But the thing is, when we treat water, you need a much bigger tank, right? You have a lot of water you have to deal with anyway, so you have a much bigger anode tank, then you have a much bigger flow through. So the overall current can match up with the current on the smaller cathode, right? It's not only the density side, it's not the same size. So that would be able to support the cathode reaction.
Yeah, so you need a much
Yep.
current. Yeah.
Yep.
It's actually from Richard and yourself. Question I have about the VFAs. We're doing a project on VFAs, but in a different route from what you guys do. But I understand from the presentation that you've got the CO2 and you've got the acetyl CoA, that creates your acetic acid.
Mm-hmm.
And then after that, you're then building up to propionic, which is whatever. What are those mechanisms, and is there competition in the production and yield of those? And do you see things like azeotropes in the more colloidal soluble ones versus the partial ones? Because the real money for us is valerate capillaries, for sure. Butyrate, you can use it to animal feed. Acetic acid is very useful. But I just kind of trying to get my head around how such a system would be built and what the soup looks like from the separation.
That's a very good question. So varying and cuprate are not very easy to not use volatility. I agree with you. So that you probably need to think about that. Is using a little bit different approach. I haven't got there yet, I have to say. In terms of the production of the different things, how would you choose? There's been multiple choices. One is sort of genetic modifying the single strain of bacteria, right? There's a Clostridium, right? There's other acidogens and those things that have been really the synthetic biology front of it. The other one is like a microbiome. How would you train Eileen actually just did that, sort of doing a sort of co-culture of bacteria to let them compete and then have a dominant culture to produce things. Regardless, either way, you have a mixed product, right? So in my view, we always think, okay, one-stop shop is always easy. You got CO2 into, say 6, say 8, that's better. In reality, unless you have a super strain of, I think it's pretty difficult. And also, in my perspective, even though I'm an environmental engineer, I really fully believe in chemical unit operation. That's the most efficient and easy to scale up, right? The more complex the system can be in one-stop shop, it's very hard to scale up. So you would probably do stepwise to do chain elongation. To me, that's probably the easier way. Then you have probably easier separation as well. So, yeah.
But it's more building block than actual.
Yes, exactly. Yeah.
Any other questions? I have a question. So for the membrane separation for the acetate, Is there any like limitation with the concentrations or?
Yes and no, depending. I mean, I have to admit, for all the current research, at least I've read, the concentration we produce very low.
Yeah.
Right? Majority, 99.9% of water, to say, right? So there's two ways. So the things we try to do is we extract, because of high volatility and basically Henry's constant in ways that you actually have this volatile fatty acid evaporate out through evaporation. On the other way, you can basically use nanofiltration to push the water out, right? So there's two approaches what you can do, there's also in the middle, people try to pre-concentrate the thing. Like whether it's URO or other things to basically concentrate the acid first and then separate them out. Because you have very low diluted reaction, that will be difficult, yes.
Great, thank you very much.
Thank you.
Yeah, any other questions? Yeah?
You mentioned about the electrocatalytic membrane. I didn't understand fully. Explain, is it a catalyst-coated membrane or membrane function as catalyst?
Yes, so it's basically coated. So basically you have a, say for example, PVDF, whatever we do most like a gases-based membrane, right? PVDF, then have a very typical one, we have basically carbon black, and then we have catalyst on it. So it's a coated membrane. It's very hard to manufacture directly.
Interface. Is the membrane conductive or are you using conductive membrane or just normal?
Most conductive membranes, at least the polymers, we've tried all the different things. You can use conductive polymers. The conductivity is not good enough to do, again, larger scale applications, right? Then the most polymer membranes, they are cheap, but you can basically coat a carbon nanotube or graphene sort of layer to be conductive, or even like a copper nanoparticle stuff to make, then you have silver, copper, whatever sort of catalyst on
But
that.
I think the stability, probably to speak, is you got so much volume of wastewater go through. How long it can last?
The catalytic membrane side does, at least if you have two-chamber reactor, does not face the wastewater.
Oh.
It's a still CO2 and hydrogen and the other cathode side. Yeah.
Great. Thank you very much.
Thank you.
Jason.
My name is Shahid.